Hello, students. It's time for us to tackle the ideal gas law. PV equals nRT. With this, the latest of the gas laws, we can not only find pressure, volume, and temperature, but we can also do something truly remarkable. We can reliably estimate about how many tiny invisible particles are present in a system of a gas. That's right. Whether we're talking about individual atoms or molecules like CO2, with the ideal gas law, we can estimate about how many are actually there. It's really remarkable. It's great, and I want to show it to you today. So the ideal gas law is PV equals nRT. And this is for units that have to be specified in advance. That is, in order for the equation to work, we have to not only say that P is for pressure, but we have to say what unit we're using for pressure. So typically we use units of atmosphere, liters, moles, Kelvin. That is, we will have a unit for the atmosphere for pressure, and it's simply 1 atmosphere. And we're going to multiply that by the number of liters that we'll get at standard temperature and pressure at 1 atmosphere and 273 Kelvin, which is 22.4 liters. We'll divide that by 1 mole multiplied by 273 Kelvin. Now, it is possible to use units of pressure other than 1 atmosphere, or units of temperature other than Kelvin, or units of volume other than a liter. It is possible, but practically speaking, in our course, the easiest way to do is to use units of atmosphere, liters, moles, Kelvin. Now, when we do that, R, which is part of the equation, R, the gas constant, is going to equal 0.082. That is, if we have 1 times 22.4 divided by 1 times 273, we get this number. So when we put this number into equation, we say 0.082, but what it is, it's really 0.082 atmosphere liters, moles, Kelvin. So all these units, the atmosphere, the liter, the mole, and the Kelvin, they're all attached to this constant R. If we were using different units, it would be a different number. But most of the time in this course, the number is going to be 0.082. So this is a number that students have to memorize. And you will see in every problem that we do in this video, every problem, we will use 0.082 for R. Now, if you're not clear on what I've just said, remember that in other gas law problems, we cancel out units. You will see a lot of units pretty much automatically disappear when we do an ideal gas law problem, automatically. Why do they disappear automatically? Because the inclusion of this constant automatically allows us to get rid of any units we don't need, because it has a combination of units attached to it. 0.082 atmosphere liters divided by moles Kelvin. So that's the big general idea. Let's say we want to solve for an unknown pressure, okay? And let's say that we have a system that has 10 liters of volume, and it has a temperature of 300 Kelvin, and we know the number of moles of the gas. And for convenience sake, we're just going to say it's 1 mole, okay? So what is the pressure? Well, we set it like this. Notice that I put P and V on one side, and I'm putting N and T on the other side. Well, that's because the expression itself is PV equals nRT. So now let's plug the numbers in. Of course, since P is unknown, we're just going to write P, and next to it, in parentheses, 10 liters to represent our volume. And then N is the number of moles, so that's just 1 mole. R is always 0.082. And then our temperature is 300 Kelvin. Now we have an equation we can solve. We want to isolate P, so we're going to divide that by 10 liters here. But whatever we do to one side, we have to do to the other side as well. Obviously, the 10 liters completely cancels. Less obviously, since 0.082 contains units of atmospheres and liters and moles and Kelvin, there's already a mole and a Kelvin in here. On the bottom, there's already a liter on the top. And so the moles, the Kelvin, and the liters will all cancel. This becomes an equation you can solve. Simply 1 times 0.082 times 300 divided by 10. And we get done doing the math, and the math says that our answer is 2.46. Now you may say, well, 2.46 what? Well, we're solving for pressure, and the pressure is always in the unit of the atmosphere. So this is 2.46 atmospheres. You can pause the video right now just to write out the setup the way I've shared it with you. Let's now have a problem where we're going to solve for volume, where volume will be the unknown. We'll say that the pressure is 1 atmosphere. This time, let's say that we have 2 moles of a substance. Let's say that the temperature is a little colder, 200 Kelvin. All right, so we set her up. We have 1 atmosphere times an unknown V equals 2 moles, 0.082, there's that number again, times 200 Kelvin. Well, again, we want to isolate V, so we're going to just divide both sides by 1 atmosphere. Obviously, the 1 atmosphere cancels. Since R, 0.082, is based upon units of atmosphere, liters, moles, Kelvin, well, I got a mole and a Kelvin on the bottom, actually, so I can get rid of mole and Kelvin, and I've got a atmosphere on the top, so I can get rid of the atmosphere. And so this just becomes 2 times 200 times 0.082 divided by 1. All right, so, and we get exactly 32.8. Since we're solving for volume in units of liters, that's 32.8 liters of volume. Again, I will suggest that you pause the video, so if you need to copy down this example, you can solve for it. Let's do that now. Okay, so now we're going to solve for temperature. We're going to make temperature our unknown. Our number of moles, we'll say that we have 3 moles this time. We'll say that we have a volume that the sample occupies 5 liters and that we are at a pressure of 2 atmospheres. All right, so here we go. We're going to set up and solve. 2 atmospheres is the pressure. 5 liters is the volume, PV. That's going to equal N, which is 3 moles in this case, times the same number, 0.082, and our temperature is unknown. In this case, we want to solve for an unknown on the right-hand side of the equation. We want to isolate T. 3 moles and 0.082 are obnoxious. We want to get rid of them. So we're going to divide this side by the same thing. But whatever we do to one side, we have to do to the others. Now, this, of course, completely cancels. Now, remember, R contains units of atmosphere, liters on the top, and moles, Kelvin on the bottom. So I've got the ability to cancel out my moles, my atmosphere, and my liters because they're built into R, which is right here. So this just becomes 2 times 5 is 10 divided by 3 times 0.82. Get done with that, I have 40.65 Kelvin. Again, I have to emphasize that the presence of the R, which is 0.082, whenever you see 0.082, it contains with it this mixture of units. In this case, since 0.082 is on the bottom, the moles and the Kelvin are actually on the top, and the atmosphere and the liters are on the bottom. And so we can cancel all those units on the left-hand side of the equation. And since the unit we didn't cancel is Kelvin, the answer is in Kelvin. Now, we've solved problems for pressure, volume, and temperature before with the simpler gas laws that were taught earlier. So perhaps you're not that impressed that we could find the pressure in atmosphere, the volume in liters, or the temperature in Kelvin with this. But now we come to the thing that the ideal gas law can do that none of the other gas laws can do. The ideal gas law can deal with the situation where either this number N is unknown or whether it changes. The previous gas laws require us to assume that our system is enclosed, that the gas doesn't leave nor does more gas enter. The amount of gas doesn't change, and we just ignore the amount of gas, the actual number of molecules. We just measure the pressure, the volume, or the temperature of the system. But with the ideal gas law, we can solve for N. We can actually figure out how much of the gas is present. And that is really remarkable because a lot of gases are odorless, colorless. They're made of a whole bunch of tiny particles too small to see in constant random motion. And yet somehow we can figure out how many are present. So let's tackle that now. Let's say we have our pressure given. We're going to say that our pressure is 1 atmosphere, nice round number. We're going to say the volume is 10 liters. We're going to say that the temperature is, say room temperature, 300 Kelvin. And it's the number of moles of the gas, which is unknown. Okay, the way we set up and solve is like everything else, P times V. So 1 atmosphere times 10 liters is P times V. And that's going to equal some unknown mole N times the universal gas constant, 0.082, the same one we've been using the whole time, and the temperature is 300 Kelvin. And we want to solve for the number of moles N. And so these two numbers next to N are obnoxious. We need to get rid of them. 0.082 on the bottom, 300 Kelvin on the bottom as well. But whatever we do to one side, we must do to the other. Now remember, 0.082 contains units of atmosphere, liters, moles, Kelvin. Since we put the 0.082 on the bottom here, that side completely cancels. But we now have atmosphere, liters on the bottom and moles, Kelvin on the top. So since there's atmosphere, liters flipped, we can cancel the atmospheres, we can cancel the liters, we can cancel the Kelvin. This just becomes 10 divided by 0.082 times 300. 10 divided by 0.082 times 300. All right, so when I do that, I'm going to get this estimate, which is, now of course, the mole, this unit is actually a stand-in for a very large number, which is Avogadro's number, 6.02 times 10 to the 23rd. And this is where our calculator becomes really essential. So we can stop here with whatever the gas was. If we said it was hydrogen, for example, this would be 0.407 moles of hydrogen gas. We can stop there, but we can take one more step. We can do another conversion. We can use Avogadro's number. So we can take our result from this calculation and write it as a fraction over 1 like we often do. And we can remember that if you have 1 mole of any substance, whatever it is, you have 6.02 times 10 to the 23rd particles of that substance. The particle could be an atom, or it could be a molecule of some sort. Let's just say that this was moles of oxygen. So for every mole of oxygen, we would have 6.02 times 10 to the 23rd atoms of oxygen. Our moles of oxygen are going to cancel out, and this just becomes 0.407 times this very large number. So let's do that. 0.407 times 6.02, and we use the E key here, raised to the power of 23. And when we get done, we have an estimate for the number of particles which are present. In this case, there would be 2.45 atoms of oxygen, or sorry, 2.45 times 10 to the 23rd atoms of oxygen. Now, this is an extra step. We took the result of our calculation, we found N, right? N equals 0.407 moles of whatever gas we're looking at. But with just one extra step, you can convert that number of moles, and then you can get a very good estimate about how many oxygen atoms are actually there. How did we do it? By using the ideal gas law. We solve for N, we simply multiply whatever we get times Avogadro's number, 6.02 times 10 to the 23rd. And there's the trick, the remarkable trick. Okay, so these are all the different types of problems you can solve with the ideal gas law. You can solve for pressure, volume, temperature, or the number of moles. And you can do this because there's a term inside the ideal gas law, R, which is based upon units of pressure, volume, moles, and temperature. When we set it to atmosphere liters, moles, Kelvin, R is always 0.082. If we use different unit for pressure, we might have a different number for R. But in this class, unless I tell you different, R will always equal 0.082. And so this is the number you must memorize to use this equation effectively. I hope that was helpful, and I believe you can do it.